Log on, tune in, find out. Another good idea from Cambridge.
Thanking the organizers for the invitation. So I changed the title slightly. Instead of coarse scale model, I put the multi-scale model reduction. It's a pointer here. Okay, so this is a joint work with Juan Galvez, who's a postdoc at Texas A&M University. So in this talk, I basically will look at a simple equation, just a flow in porous media. So this is a linear flow equation in porous media, but where the kx is a highly heterogeneous, especially the heterogeneity that we observe in subsurface formation. So typically what you see there, first of all, there's no scale separation, no periodicity whatsoever. And there are many scales, there's not a single scale, but there's also a high contrast. For example, this is a typical, for example, fractured rock, and you can see that, this is a hammer, just to get an idea of the scale, and you can see that here you have fractures where the permeability, where this kx inside a fracture will be very, very high. And in a rock, it's very, very small. So there is a very big jump in a K. So in fact, it's as big as your small scale. So this problem has a spatial scale, say epsilon, just like you saw in a previous talk. That will be a width of this fracture. And the jump in a K is also of order of that width. So it's very, very, very large. And I think these are the two really scales you can encounter in this type of problems. And the other one, for example, is a benchmark test. I just put the SPE10 posted by SPE, Society of Petroleum Engineers, for benchmarking upscaling results. And you can see here, this is a larger scale. This is each grid blocks on a many meter scale, but this is a log of the K. So you can see that it has very high variation, and moreover, it has a very channelized structure. So just like in a fracture, you can have a network, but it's not clear whether this network connects or not. So, so again, in a talk, I'm going to assume K has a multiple scale, no scale separation, and very high jumps. And the goal will be to develop coarse scale model on numerical homogenization, as you saw in a previous talk. So in this problem, one of the things which is important that you know, when you start building this reservoir model, subsurface model, they tend to be very highly detailed, many grid blocks. Like for example, reservoir model can be 1 billion grid block, and then it's very difficult to solve this problem on a fine grid and to do a lot of time what's called optimization. For example, I'd like to place the well somewhere and try to figure out where to place the well so I increase the oil production rate. This is an optimization problem. So you're solving many forward problems, and you'd like to solve them on a coarse grid. So here in this talk, I will basically do the reduced models, come up with some multi-scale, some coarse scale models, and also discuss their application to preconditioners. That's where you also need a coarse scale. So let me start with a very basic coarse scale model that probably everyone can understand. So if I have an image just like this can be my permeability field. So that the very simple thing you can do, you can say I'd like to coarsen it from 64 by 64 to say 8 by 8, such that I preserve the image quality. This will be the simplest thing you can think of. But even you think about how you do that. When you do that, you have two different field. You have a field at two different grids, so you need to map them to a common space so you can compare the results. And in our case, basically, common spaces are quantities of just like an average solution of PDEs and etc. So permeability itself has no meaning in a sense, because I'm interested coming up with a reduced model that give me the same average responses of the solution. Okay? So simplest procedure, which has been used for many years and still being used, it's a local upscaling homogenization. So I have a fine grid, so these fine lines represent the fine grid, and then every fine grid block there is a permeability. Then I have a coarse grid that is a union of the fine grid blocks, and a goal here, for example, in this one, I have different permeability in each block, so I'd like to replace them by one single permeability called upscale permeability. So this is done typically. What you do, you go to the local cell you solve the local flow problem, divergence k grad phi, subject to some boundary condition, for example, linear boundary condition. Then you come up with some quantities of interest, an average integrated response, for example, average energy. This is a single quantity. Then you ask the question, if I'd like to find a k star, so that if I solve this problem with exactly the same boundary condition and compute the same quantity, I'd like these quantities to be the same. And that will give you expression for the upscale permeability. And this is basically another way to do the homogenization. So what we're interested, so in this case there is already, still you see a concept of permeability, right? But my goal is just to find a reduced model for the solution. So I'm not interested in permeability because I measure, say, oil production rate and quantities like this. So we're interested basically approximating solution of this equation given on a fine grid. Again, this is a fine grid, little lines, and this is my coarse grid. It's a connected union of fine grids. So given a solution on a fine grid, pi phi versus fine, you see, I'd like to find representation of this on a coarse grid with some basis function, which is really the main core of the talk, such that this difference is small given a coarse grid. So this is a problem I'm trying to solve here. So but the main questions come up: how to determine this basis function, phi, how to make sure I don't have too many of them, because I can put many of them and make that error small, so I'd like to have very few of them. I'd like to be able to control the accuracy, and I will show that actually the coarse spaces, in fact, first thing I will show that coarse spaces are important for preconditioner, because you will not get optimal preconditioner if you don't choose your coarse space correctly. Optimal in a sense I will define. Let me start with a very simple multi-scale find element method to introduce by Babushka, and then Hao and Wu generalized it and really used for a heterogeneous problem. So assume that I have some basis function on a coarse grid. So again, this is my fine grid. You see, this is fine lines are fine grid. This is bold lines are coarse grid. So for each node, I'm going to define a basis function. Let me start with a very simple basis function, where I will basically take the nodal value here 1 linear. So I take the bilinear basis function and just keep the values on a boundary and solve the problem, solve the homogeneous problem inside, just like this. So basis function here for this node will be 1 here, linear boundary condition. It's 0 on the outer edges. It linearly goes down, and inside each coarse grid block, there are 4 of them. The homogeneous problem is solved. So each basis function satisfies divergence k grad phi 0 in omega I. This is my omega I node I, and phi is equal phi 0, it's linear on a boundary condition. So once I determine this basis function for each node, then it's just the Galerkin projection. So I have the representation of the solution P in terms of this basis function Ci phi. Then I substitute into the equation, right, and multiply by test function, and I can get an expression for these Ci's, and that will be basically my coarse solution. Ci will be in this case pressure at the coarse node. So this multi-scale method has similarity to upscaling. Still, there are certain features of upscaling. Upscaling goes back many years. Even the Darcy law is an upscale law that I like to preserve here, and this is very crucial. For example, in upscaling, we compute the local effective parameters that we reuse for any right-hand side, any right-hand side or any source term on boundary conditions. So they're like effective properties of the media. So in the multi-scale methods, in the one I just showed you, and I will stay with that framework, basically these effective properties are in terms of the basis function. So this basis function can be reused no matter what source term I have, right? And if permeability, if properties changes in few blocks, I just need to change basically a few basis functions, if I can. So, but there are some advantages of multi-scale method over the upscaling. I listed some of them. The main one actually is this one, which I will come back, that in this multi-scale methods, I mean, you can definitely recover fine scale features, but there also you can impose many basis function per node. In upscaling, it's a little bit not clear how you can actually have several upscale permeability in each grid block. But both methods suffer from the same both methods need actually very careful local problem setup. For example, in a multi-scale method, if you remember, I mentioned that the basis function is 1 here and that boundary condition linear. But the boundary condition is very important. In fact, the boundary condition should be somewhat consistent with how the fine scale solution look like, because fine scale solution is oscillatory, and I impose linear boundary condition along the edge. So when I rebuild that solution back, my solution in fact going to be linear along all these edges, just like you see here. Here I have a permeability with a 9 high. This is a high values. This is low. So there's a 3 by 3 grid. So true solution look like this. And you can see along the edges here, they're not linear. They actually have a very special form. But if I use a basis function, the one that I mentioned before with linear boundary condition, then solution along the edge is linear, and then that introduces pollution effect, like as Sir talked about it. It can give an errors of order epsilon over h. So for example, if I have a small scale epsilon and a coarse mesh h, then basically these errors usually in a periodic case can go as an epsilon divided h. So it can be very large when the spatial scale become comparable to the coarse mesh size. Or you can have here, in this case, I mean, there's only one, you can have a lot of oscillation here and you will be replacing them by linear. So it's very important to come up with a right boundary condition when you do these problems. And this is a little bit background material. So there have been and actually with this I probably this is more of a literature review. So there have been a number of ways to improve this thing. One is called oversampling method. So as we, I don't want to impose linear boundary condition on a coarse grid block. So instead what I do, I pick a larger domain where I solve the local problem in a domain S with artificial boundary condition, the same linear boundary condition, but then I remove the part that is between S and K. So these are this type of approaches over sampling. They're actually in Trelm industry, there are different names, border region method and etc. So been introduced. So this way you stay away from the artificial boundary condition and you use only internal information of this. So when you solve this local problem in the region S, you just take the information in K and throw away everything outside. And then there's a little bit, you can even go to the bigger regions. Maybe Homan will talk about it. There are approaches where you can couple local with global and etc. So the question I'm interested in, can we add the basis function so that this multi-scale method converges to the fine scale solution in some optimal way? So here's some literature review. Just to be fair. So the multi-scale finite element method. The application to the subsurface requires some mass conservative methods like a finite volume, mixed finite element, and people, there are a lot of issues like stability and all that you have to deal with, and then then there have been like mixed multi-scale fine volume methods. Then the methods I mentioned. So many of these approaches in this list use a subgrid model, just a like subgrid model with linear or periodic boundary conditions. So which is from the subgrid point of view, these models share a lot of similarity. But when you come once you build this basis function, then how to couple them, they can be quite different. Just in a couple of slides, I just want to say something about application. I'm not going to touch this here. So typically, what do we do with this coarse scale model once we build them? We use them in a subsurface flow and transport. So simplest case will be two-phase flow and transport. So this is a flow equation for P, and then you have a saturation of, say, water phase that is controlled by this equation. So these equations are coupled. So what do you do here? You take S at initial time. So what the workflow is the following. You take S at initial time, you build a basis function based on K, and then you use flow equation on a coarse grid, compute the fine scale velocity, for example, and you update your saturation front, and then you go use the same basis function you have to solve pressure. Each time pressure equation solved on a coarse grid, so basis function not updated. Each time basis function not updated, and this is, for example, where even without changing the source term, that gives you some gives you speed up. Now here's just a test to show how the locals method, what will happen if you just take the local method. This is a bench. This is that SP10. So it's a 220 by 60 field. So you inject from the left and produce so you're basically injecting water here and producing oil here. And you can see here this is a water saturation. So you have inside the channel most of the thing propagate. So here if you use a local basis only, so in this case you can see that there are arrows here. So local basis don't see the connectivity at this corner, so it introduces arrows, and there are arrows here. So if you use bigger, you can really make this much more accurate. For example, here we use a larger coarse blocks, and it's much more accurate saturation profile. So this is another issue in this case, and I will finish with this. And it's another issue is gridding. Coarse grid. You can play with a coarse grid. You can build a very, you can optimize your coarse grid based on heterogeneities. And this is, for example, we have worked with York, Arnett, and others. So you can, for example, in that SP10 I showed you, if we optimize, like this will be my coarse grid. So coarse grids can have very, very strange shapes. So here fine grid is a Cartesian grid, but what you see here, these are my coarse grids. So random color assigned to each coarse grid block. So sometimes you have to really get the coarse grid tuned. So if you want to actually make this approach is more accurate. But this is a little bit of overview. So now how the coarse scale spaces come in at the domain decomposition preconditioners. Let me just in one slide. So I have a fine space. This is piecewise linear function that lives on a fine grid. So there's NF is the number of degrees of freedom on a fine grid. V. So my Galerkin system, Galerkin linear system will have the following form: AU equal B, where AU is just the fine scale, what I call stiffness matrix, a K grad phi grad phi j. And if I have a coarse space phi I, right, then I can build a coarse space exactly the same way. AI J0 will be K grad phi grad phi j. So when I was talking about multiscale, upscale, and our goal was to make sure that we would like to reduce the error U minus U0. Right? And as I mentioned, U minus U0 depends on epsilon over H. Epsilon is a small scale, if I have one small scale, for example, and H. But it also depends adversely with a K max over K min, maximum of conductivity divided minimum conductivity. So we have another choice whether we can add more basis functions. So how to get to the exact fine scale solution? If I want to, I can either add more coarse basis function for each node, right, and then converge, or I can iterate on residual. So that will be like doing a preconditioner exactly. And in this slide, so basically to iterate on a residual, for example, let's say additive Schwarz. So what you do, you compute this coarse solution, right, and then I compute the coarse solution, and then I can downscale with my basis function. Then I can compute the residual, and then I go correct the solution in each coarse grid block, just shown here. So this is my coarse solution. Then I can compute the residual on, let's say, 2 by 2 coarse grid blocks, and I go to each coarse grid block and correct the solution. So in that sense, so then this is an iterative process, and for example, this will be very similar to the additive Schwarz preconditioner. Right? And the preconditioner itself, it's written here. So you see first term here, if you know, this is basically solving problem on a coarse grid. So you project on a coarse, R0 is a projection to the coarse space, solving on a coarse grid, and then projecting back to the fine scale. And this is the local solve. AI1 is a local solve, and this is just cuts the solution to the local domain and extends to the whole region. So in a preconditioner, you'd like to have a condition, you would like to control the condition number. So condition of B minus 1A we want to be less than some constant that independent of contrast. Remember, contrast can be very large, so we'd like that to be independent of contrast. So number of iteration here in this procedure is basically represented by this C. Right? So if you don't pick the coarse space correctly, if you pick just the multi-scale coarse space is the one I showed, what's happened that this C, the condition number, it become proportional K max over K min, and anyway, it can be infinite. So you need infinite iterations almost to converge. So the same, so coarse spaces I will discuss, they basically will be both precondition and multi-scale coarse scale approximation. Okay? So again, the goal here to have, we have two parameters, small spatial scale and a jump. So we'd like the method basically to converge independent of these parameters. I'm looking at the composition precondition. I'd like condition number to be independent of the contrast. Or multi-scale method, I'd like it to converge independent of this small spatial scale or a contrast. Right? I mean, here I just put an example to warn, like, you can write a CI's lemma and you have the convergence at H, but the fact that this second derivative of P, it's very large. It's both adversely affected by the spatial scale and the contrast. So now in domain the composition preconditional literature, there also been a lot of work, and most of the work, a lot of work focused on a smooth coefficient. There've been quite a few work, many work also when your coefficients are what's known as a piecewise heterogeneous. So within each block, I have almost homogeneous coefficient, but I can have a big jump from one coarse block to another coarse block. This case is also analyzed extensively, but not much actually done for a general heterogeneities when your coefficient can have a lot of variation within the coarse grid block. There have been some work by Arnes, and but there's a work by Graham and Rob Scheichel actually, which really motivated us to look into this. But there's cases where within each coarse block, assume that the heterogeneities are basically just an inclusions, and you can just do one basis function, just like I showed, to come up with an optimal precondition. So when I say optimal precondition, I mean the condition number is independent of the contrast in a jump. So how do we build the coarse spaces? This is the first step. So let's look at this eigenvalue problem. So divergence k grad psi I equal lambda I k. So the weight here is very important, the k. So if you look at this problem, and let's look at this type of heterogeneity. So this is a coarse grid block. Inside a coarse grid block, I have a high conductivity channel. I have two high conductivity channels. These are channel, and I have a 4 inclusion. So if I look at the spectrum of this eigenvalue problem, I will have exactly, so within each this high conductivity region, I have a lot of fine grid blocks. But if I look at the spectrum, I will have exactly 6 small eigenvalues. Small, they will go actually, if this is 10 to the 5, they will go 1 over 10 to the 5, 10 minus 5. I will have 6. Then I will have a big jump, and I will go to the eigenvalue of order 1. Okay, so next one will be order 1. And you can see that, for example, from this Rayleigh quotient. So what is, so numerator, if you look at the numerator, so if I have the function that are piecewise constant inside these inclusions, it basically glues the inclusion together, then the numerator is order 1, while denominator very large, because k is large while psi is constant. So you have a number order 1 divided by a very large number, so it ends up being a small number. So what this does basically, it allows to glue together all the fine grid block inside, and you're trying to represent all the piecewise constant function that lives inside this inclusion. So, but if they get connected, right, then you have one region where you're just trying to represent piecewise constant functions. Okay? So you can see this is the eigenfunction. So first eigenfunction is piecewise. So it's basically it's a linear inside the 2 channels, and you have a bunch of them. They basically represent all piecewise constant, and you have totally here 6 piecewise constant. So this is again the case when this inclusion somehow separated. There's a clean big jump in a spectrum, but you can have cases when a gap is not very clear. So if I take this coarse space, how do I build? If I take this eigenfunctions, how do I build a coarse space? It's a following way. So I go to each coarse node. This is my coarse node here. So for this coarse grid block, I will solve the eigenvalue problem I showed you with that weight k. And I compute these eigenfunctions. I will have, for example, let's do on this example, let's do on this special case. If I go to this node, I take this 2 by 2 block out. I have 1, 2, 3, 4, 6 separate high conductivity regions. So I will have 6 small eigenvalues. I take each of these eigenvalues, so they will have a shape like this, and I multiply them by partition of unity function, which is a function that is 0 on the boundaries of this on this 2 by 2 block, and they sum up to 1, for example, bilinear function, and that will make them 0 on a boundary. That's why I have a continuous Galerkin method. And then span those basis function, and this will be my course space. So then I go for each node. So each node I do the same thing. So go to this node, and solve that eigenvalue problem, and pick the eigenvectors that correspond to the small asymptotically vanishing eigenvalues, and multiply them by a partition of unity function. And this will be my course space. So then you can show, for now I just showed domain decomposition result. So you can show that actually condition number of this preconditioned matrix, the number of iteration in that procedure is independent of the contrast. In fact, it will be C divided the eigenvalue you left out. So there's a one eigenvalue you left out. You did not include the corresponding eigenfunction. The condition number will go C over that eigenvalue. So in fact, if you left something small, then condition number will be infinitely large. And to prove that, typically you prove something like you show that the weighted L2 norm is bound. So you have to bound the weighted L2 norm by the energy, and this coefficient in front of it. It's what's basically coming a condition number. Okay, there's one thing that the condition number. I mean, we're interested just to make sure the condition number is independent of physical parameters. There's a numerical parameters, which is a coarse mesh and overlap. And if you notice, I took the overlap to be a size of the coarse grid. So overlap is actually order h. So this number is order 1. So this says this precondition is an optimal. It's independent of any physical parameters you have. And again, the contrast come here not because of jump in a coefficient, but also in a small scale. Because within the coarse grid block, if I have a lot of variation, this is unavoidable. And the only way to get the variation if I have both small scale and a contrast. Let me show you a result first. So this is conductivity. You see here, have a high conductivity in these inclusions. And what we're going to do, we're going to increase this conductivity and see how the condition number changes. So background blue is conductivity 1, and conductivity very high in these inclusions. Okay. So here's some of the number. So what you see here, this is number of iterations required for convergence, and here you have a condition number. So if I choose a linear basis, just a linear basis, here I pick a multi-scale basis, the one I showed. So each node you have that one basis function. You solve the problem locally, and there's an energy minimizing basis. Basically, it's again a basis for each node. The limits differentiate. So there's this basis multi-scale energy minimizing. You have a one basis per coarse node. Each node has just one basis. All the other approaches, the one that this two I propose. So there are many bases per node, right? So energy minimizing basis, you're minimizing this energy of all the basis functions subject to this, that they sum up to 1. So if you see that all this method, as you increase the contrast, the basically condition number grows. And in a limit, in a very high conductivity case, this can be very, very high. While if you choose coarse spaces carefully, then a condition number remains constant. What's that? I come back. Let me just. So let me just now go one thing. There may be there's something here still with this basis function. Let's look at this example. This is my coarse grid, and within coarse grid I have a lot of inclusion. Assume that the size of the inclusion is epsilon. Coarse grid size is capital H. Then total number of inclusion will be h squared divided epsilon squared. So for us this is infinity. So basically, if I use the method I showed you before, I need infinite dimensional coarse space in order to make my preconditioner optimal. Right? So there's we want to avoid that, because this is typical. For example, in a typical case, you can have a lot of inclusion just sitting there. Even doesn't have to be epsilon or h. You can have a lot of in a fractured network. You can throw a lot of fractures that don't talk to each other, and then you're just trying to represent them on a coarse space. And you probably don't need it, and that's what I want. I will show you how to avoid that. So inclusion. Let me actually. I'm going to use this word a lot. So when I say inclusion now, it's something like this. So it sits inside a block. It doesn't touch the boundary. It's isolated. It sits inside the block. And then there's a channel. That's a high conductivity region that connects one boundary to another. Okay? Channel is a high conductivity region that connects one boundary to another. So how to reduce the dimension of coarse space. So I'm going to come back but show that intuitively what we want to do. We want to remove the inclusion, but we cannot remove the channels unless we know something beyond the coarse grid block. So in other words, if I have a coarse grid block like this, in this case I have 7 inclusions and 2 channels. So what I'd like to do, I'd like to lump all these 7 inclusion into one basis function, but then I have to have 2 separate basis functions for each channel. So how can I do that without going and manually just detecting those inclusions? I'd like to do it in an automatic way. And again, intuition here, if you for example work on homogenization, you know that, I mean, things like inclusions, their effect can be localized, right? Even if I have many of them, I probably can localize them with a single basis function. So let me show you how to do that. So let's start. Let's say that I take a multi-scale finite element basis, the basis I showed you before. That's my chi-i. That's my local cell problem. So for each node here, I have a multi-scale basis function. And this slide probably very important. I put everything in one, but it's so in each node I have a multi-scale basis function, right? In each node I have. Then what I do, I take the energy, pointwise energy, and sum over all coarse grid block, over all coarse nodes. So I go to this node, I compute the pointwise energy. I go to each coarse node, I compute the pointwise energy, and I sum it over all the coarse nodes. Okay? So if I had a multi-scale basis function and I had this inclusion, what it's going to do, so if you think of the solution, okay, this is isolated inclusion, so solution will be constant inside the unsulated high, though it's a conductivity is high, but it's isolated, sits on the background of low conductivity, so solution will be constant. So when I look at this function k tilde, actually it's going to look exactly like this. You will see no inclusion. It will kill all the inclusions. On the other hand, if I go to this case where you see there's some inclusions here and some channels, so this is inclusion, some channels, so it's the same multi-scale basis function. If I use, for example, basis function here, this is a channel, so it's not going to kill because the basis function, remember, it's 1 here, it's linear here, it's 0 here, so there's a pressure, there's a gradient going that direction. So you will have this gradient chi square going as a 1 over h, right? And then you multiply them by a large number, so you cannot kill the large number. So that's why you can see that when I look at the k tilde, all the channels are present, but all the inclusions are removed. Now let's go to if I just had a bilinear function, just a linear basis function, what will happen? I will just get exactly the same picture, just a risk scale, right? Because if I have a linear basis function, grad chi is a constant, I'm just doing nothing, I'm just summing up the k, so I will not kill any high conductivity region. Okay, so once this is a weight function, and the weight function very important. I mentioned in the beginning, for us the weight function in eigenvalue problem is the most crucial thing in constructing the basis function. So then I put the weight into the local spectral problem as a k tilde. So you start with some partition of unity function. You compute the pointwise energy sum over all coarse node, compute this k tilde, and put in a weight function. So now if you can think that what will happen, for example, in this case, there will be, if I go to each coarse node, there will be only one small, actually one thing I forgot, this eigenvalue problem I solve with 0 Neumann boundary condition. Right? So if I go to each, so if I have a homogeneous permeability, then only small eigenvalue will be 0 and corresponding eigenfunction will be 1. So my coarse space will only consist of this basis, multi-scale basis function here. But if I go to this cases, so what will happen, that all basically I will do what I showed you before. I will basically incorporate effects of all small inclusion into one basis function, lump into the one basis function. Then when I solve this problem, the only small eigenvalues, the eigenvalues that are small, the corresponding eigenfunction will represent the channels that connect boundary to boundary. And those are basically, I will argue that you need to have them on a coarse space. If you go back a little bit, I mean, basically the goal will be, you can start with any partition of unity. The objective is to make sure that k tilde is as small as possible, right? And for example, multi-scale basis so it's very important to start with a good initial basis function. So initially, if you don't have a good initial multi-scale basis, then what's going to happen in your coarse space, you're just going to have the things you could have localized, you could have lumped them together, but you didn't. So you have now a high coarse space, and it can be infinitely high. So in that, it's again, we can show that condition number is independent of contrast. Condition number B minus 1A in this, if you choose that space, is independent of contrast. So now let me show you numerical examples. So this is a permeability field. This is a coarse grid. I think fine grid is 100 by 100. This is my coarse grid. So this is how K tilde will look like. So all the small inclusions will be killed by one basis function. So if I look at the numerical result, again, the red regions are high conductivity, which we increase. So 10 to the 4, 10 to the background is 1. So if I choose a multi-scale basis, 1 basis per node, no. So I get the condition number is increase it 10 times as I increase the eta. If I choose a K tilde equal K, so in this case, my coarse space has all the inclusions and the channels. Very large coarse space dimension. Large coarse space dimension here is 102. Because I have both inclusion and the channels, and the condition number constant 6. And then if I choose the K tilde with multi-scale, so I remove the inclusion, I lump them into one basis function, and condition number is a 69. By the way, the fine scale, the fine scale is 80 by 80, so fine scale is about, it's 6,400. So it will be that much. So this is really not a big coarse space. So let's look at this example. So you have a one big channel inside, and you have a smaller channel, even a smaller inclusion. Again, you can observe similar thing as so if you use multi-scale or energy minimizing basis, where you have one basis per coarse node. As you increase the contrast, condition number grows, right? But if you use K tilde K, so you have a large. Actually, in this case, this is. This was a different example. Let me note. This was for the other case. I will show you later. Come back to this later. Now this was there are a number of other examples in a paper. So let's go back now. Coarse scale approximation. So far what I showed you, that as a precondition, if you use that coarse space in your two-level preconditioner, we have also multi-level, so you will get an optimal condition number. So condition number is independent of physical parameters. So this is in that sense. But how good is a coarse scale approximation? Let's look at this permeability field. We're not just look at this permeability. Let me first argue that before I argue, so there's a high contrast homogenization result. So if I'm looking at a periodic, one thing with a periodic homogeneous, actually some of them not periodic, Hohmann's work is not periodic, but if I look at a periodic homogenization, what's happened that your channel is finite. Either you have an infinite channel or you have an inclusion. Right? There's nothing between. If you have a periodicity, so we in this case we're staying away from periodicity. So high contrast homogenization. So there've been a few work on a high contrast multi-scale find element. For example, work by Chu, Graham, Howe, where they all consider a case with inclusion inside a coarse grid block. And the Beryl and the Wadi, where they have a more general case, and he will talk about it. And there've been, again, periodic homogenization. There've been some more work. But let me first argue that you need a multiple basis per node if you're doing a numerical homogenization. So here's an example in 3D. It will be even more evident that you need. So let's say I have three high conductivity channels cutting my coarse grid block. This is my coarse. If I had a one basis per node, right, what I will do, I will enforce the pressure, I will enforce the solution value among these three channels. So if I know my pressure values here, I know my bases here, I will have a correlation between the values of the bases in each channel. But in fact, these channels can go outside anywhere they want, right? So you can come up with and since you can impose any boundary condition you want, coarse scale, so you can always come up with an example. You can get all possible pressure values inside for the solution, and you will not be able to get them with your one single basis. So you need a multiple basis if you'd like to have an accurate coarse scale approximation. So here's some of the results. So that the permeability field I showed you in this slide, this is a permeability field. So these are all high conductivity region. This is inclusion channels. It's probably 80 by 80, 8 by 8 coarse grid. So what you see here, this is my fine scale solution. So it's a flow from corner to corner, so like x plus y boundary condition, imagine. So through fine scale solution look like this. So if if you use the multi-scale find element with linear boundary conditions, so this will be like a worst case scenario, and you can see that the error very large. So you can definitely tune the boundary condition, get better estimate, but that's not the goal here. I just wanna just pick one of them. So errors are about 90% if you do that. So energy minimizing errors about 25%. Actually, in some cases can go also very high. This is again one basis per node where you're just finding the basis function such that the energy, sum of the energy is minimum. And here's a different method with a spectral basis that I showed you. So so you can tune them differently. So for example, here energy, the error in energy norm 11%, 6, 10%. So what they observed that about 10% errors. So if I look at the errors here, multi-scale, so this is for different grid resolutions. So H here 1/10, I go to 1/20. So I'm not going to comment on the multi-scale energy minimizing because they're not really designed probably for this particular problem. So if you look at this spectral method, the error really doesn't go down. In the first place, error doesn't go down, and this is a weighted L2. So let's ignore this table. So what can we say about convergence rate? Actually, you can show that convergence rate. So what you can prove that the convergence rate for this spectrum with this basis function, if you pick sufficiently large eigenvalues, if you went down to you cannot. So you must have the first small eigenvalues, otherwise you cannot do anything. But you have to go even further a little bit. So if it's big enough, this lambda, then a convergence rate and an energy norm is a H, capital H, which is a coarse mesh, divided by lambda star. So lambda star is an eigenvalue that you did not. So it's a smallest eigenvalue. So you haven't we did not include some of the eigenvectors in a coarse space, right? And then the corresponding eigenvalues for each coarse grid block. So if you take minimum of all this, that's a lambda star. So it's the eigenvalue you left out, but the minimum among coarse grid blocks. So H over lambda. Then you have this term here, K. So it's a somehow residual, still a H1 residual, and something comes from the source term. There's some assumption on a source term. So source term must be some L2 function for any source term. Also, you cannot get the conversion like any source term you can. So this table, maybe just ignore. I come back and say a few things about the detailed numerical studies. So first of all, you see this term here. Since these are the spectral, this is orthogonal projection, this I0U, you know that this is less than K grad U square. So here you basically have an energy norm, right, which is this term, you have an energy norm. So if your solution is smooth, then what you can do from here, you can go even further. You can go to this from this norm. If you had that K is equal 1 and very smooth solution, then here you have an H1 norm, and you have this here, we will have a piecewise linear interpolation. So you can go to the second derivative and gain another H order. But you cannot gain H order if you're in a homogenization setting, because in homogenization setting, second derivative of the solution is you get 1 over epsilon, if you remember from the third stock. So the objective is to reach to the higher values of lambda very quickly. You want to get to the higher values of lambda with a smaller coarse space. So that's what this initial basis function do, right? They just take as many of these things you can localize, and then as I argue that you have to have the channels on your coarse space, because you cannot, if you don't have the channels, basically, you will have this lambda. So in a sense, first of all, the choice is important. This is, I'd like to point also, like if in a sense, if you, some analysis, for example, generalized find element, you try to find the best approximation in say energy norm for each patch, and then you multiply by any partition of unity, and that's what can go wrong there. That you just find, I'm not sure, but I just thought that not can go wrong, but what can happen that you can have a very, when you try to find the best approximate in each coarse grid, you may have all this little inclusion in a space, and then you multiply them by linear test functions. So this, you can end up having a very high dimensional coarse spaces. So this convergence rate here, in a sense, I'm going to put, I will show you the different table, but it's hard to say what I'm getting. But when you get to the tail, higher tail, you take more and more eigenvalues. This guy gets smoother technically, but we don't have a proof. But so I'm going to write this convergence as h1 plus beta divided lambda star. I'm going to just show you the number of beta. Is it optimal? In other words, is it optimal? Well, in terms of the physical parameters, I believe is some optimality, but you probably can make this the spectrum go increase even faster. So this is a permeability I'm going to take. So you have a high conductivities, different high conductivities, inclusion and channels. So what you see in this table, so LSM, so I use a K tilde equal K. So my course space has all the inclusions and the channels. So LSM 0, I included only the eigenvalues that are very small, that only correspond to the high conductivity region. LSM 1, for each course block, I included the next one. 2, I included 2 more, etc. Look at basically, let's just look at the first column. This is energy arrow, and this is that lambda star, the minimum of the eigenvalue. Right, so minimum of eigenvalue increases. Right, this is increases, and the arrow decrease, but sometimes it doesn't decrease fast. And here for 2 different measures, H110, 120. So if you look at the values of beta, which you observe here, remember beta 1, it will be like an optimal. It will be h squared convergence, and you know, initially, because you have a not very small beta, and then you pick up very fast. Actually, at the end, it just goes over 1. LSM tilde, so this will have a smaller course space, because inclusion, you start with this multi-scale basis function that contain all the inclusions, and this is z plus 0 means that my course space has only eigenvectors that are small. In other words, the channels, and then I add more and more, and here's the values of beta again. It's going up, and actually, if you look at the numbers, it's smaller than that in LSM. But I mean, there's no good reason that it should be smaller or bigger. But the fact that you have this convergence, you can see. Just in one slide, I mean, so what turns out that computing this local eigenvalue problem can be expensive. Right? Your course grid can be big, so your local eigenvalue can be expensive, and so you can compute them hierarchically. In fact, what you can show hierarchically means that if I want to solve eigenvalue problem in this course block, these are a lot of fine blocks, so I can solve on 2 by 2. Just take an important one and just start coarsening like this. Very fast. So you can show that actually the number of important eigenvalues, those are that are small, those are that represent the channels and inclusion, you preserve them, so you have the same number, whether you do it truly on a fine grid course on a coarse region, but use the whole information, or you do hierarchical, and this is for this case. This also led some of the showing that you can actually do the spectral AMGs for high contrast problem. You can show that if you use it as a preconditioner multigrid, then a condition number also independent of contrast. Again, I mean, I don't think the result for AMG or the preconditioner is too much about the contrast independence at a multi-scale. Well, let me finish. So reduced coarse model approximation. So what I discussed about reduced coarse scale approximation of the solution of PDE using the multi-scale basis. So eigenvalue problems basically we choose so that we capture important effects. So it's very important to start with a good basis. Good basis so that we end up having a small coarse space, so that we can localize effects. We can, and then the channels, as I argued, that you cannot localize, so we need to include them in a coarse space. And so dimension reduction for the it's optimal with respect to the contrast in a preconditioner. In a coarse scale approximation, you can show some convergence rate, and eigenvectors you can compute hierarchically, and but still, I mean, if you can think of, if you have a lot of channels, you can have a channel width is epsilon, and within coarse grid block you can have a lot of channels, h over epsilon channels cutting the coarse grid block, and basically this case will be probably not homogenizable in this language, because I will have a very infinite dimensional coarse space, and yeah, I don't know, this approach probably can't do anything. I'll stop here. Thank you.
Just two small, maybe silly questions. Question one is that can you summarize a little bit advantage in terms of applications between multi-scale methods and traditional adaptive methods like mesh refinements?
This is different because here we don't do mesh refinement. In other words, it's typical in, for example, subsurface that you have a fine grid. It's fine enough that you need to coarsen it. Actually, so there's no mesh refinement done. So you take fine grid, you've given fine grid, you've given very large subsurface model. You just want to coarsen it.
So you mean that basically multi-scale and mesh refinements are for different topics?
Yeah, you can do mesh refinement, bro. Will be just tuning your coarse grid, making your coarse grid geometry, just like I showed here. That will be adaptivity if we do, but this is probably not what you're asking. I mean, we basically try to tune. So in the main talk was the coarse grid given. So I take the coarse grid and build my basis function. Give me any coarse grid. Give me a coarse grid and we'll build a basis function. Adaptivity here will be how can I choose a coarse grid flexibly. I have a geometry, arbitrary geometry, so I can choose a coarse grid so that I improve accuracy. This is a valid question. It's a hard question. But that will be probably adaptivity for us.
The other small silly question is that any common points between, say, multi-scale methods and multi-grade method, which is traditional method? Any common?
Yeah, so multi-scale, you basically, in multi-scale, you will converge in one iteration, right? You may get a bad solution, but you converge in one iteration. Multi-grid, you may take you infinite iteration if you have a bad heterogeneity, right? So that's it. And then multi-grid, I mean, you're after a fine scale solution. Here we after a reduced model. And get some coarse space, and we just get a solution, whatever we get. So
multi-grids can be used in the same case.
No, in fact, maybe even other way. Yeah. So I don't know which way, because multi-grid needs a coarse space too. You cannot get an efficiency in multi-grid if you don't have a good coarse space. If you have a linear coarse space, you will need a infinite. I mean, in a limiting case for high contrast, you need an infinite iteration. So multi-scale, multi-grid also relies how to build these coarse spaces. But you can use ideas from multi-grid to build coarse spaces. That's right. But how good they're going to be, I don't depend on them.
Well, thanks again.
Thank you.